These videos cover Chapter 7. Remember to pause often, do the problems with me, have your spreadsheet technology ready, and pause the video often and take lots of notes. We're going to just cover some brief definitions in here before we move on. Just a reminder about population and sample. So population consists of all the items of interest, and we use the word parameter for when something is unknown. A sample is a subset of the population, and we use the word statistic when we calculate from the sample. So example 1, St. Joe's is curious about how many meals a week a student eats on campus. They surveyed 50 students. So the population would be all SJU students, because that's who they're interested in, but the sample would be the 50 SJU students that they surveyed. College Board was interested to see how many high school students received scholarships to college. They surveyed all high school students in Philadelphia. So the population is all high school students, and it doesn't even say in America. It's just all high school students. Maybe they should be more clear. And the sample would be all Philly high school students, because that's who they're actually asking. Bias can happen in all sorts of different ways. I really encourage you to read your textbook. There's some really interesting examples about bias and how that affects the sampling. And then we can actually sample in lots of different ways too, by dividing the population up by types of people, strata, or by location into clusters. And then now we're going to actually apply these sampling distributions. So when we talk about a sampling distribution, what we are saying is that we're going to be taking infinitely many sample statistics. So we're going to survey one group and then another group and another group. And if we do that infinitely many times, the sampling distribution is going to look normal. And if it looks normal, then we can do all sorts of calculations with it. So an estimator is a statistic that is used to estimate a population parameter. So X bar is the mean of the sample, and that is used to estimate mu, the mean of the population. So if you think about that St. Joe's example, we would calculate all the different means of the samples, and that would be our estimation to calculate the population mean mu. The expected value of the sample mean X bar is equal to the mean. So if we're trying to determine the expected value of a sample, we would just use the population parameter. But if we're trying to find the standard error or the standard deviation, we do this calculation. We take the population standard deviation and divide it by the square root of the number of trials. So let's do an example here. So the chefs at a local pizza strive to maintain the suggested size of their 16-inch pizzas, but no matter what you can do, there's no possibility to make sure every pizza is exactly 16 inches. So the manager has determined that the size of the pizzas is normally distributed with a mean of 16 and a standard deviation of 0.8 inches. So in general, we know that it's mu of 16 and standard deviation of 0.8. What are the expected value and the standard error of the sample mean derived from a random sample of 2 pizzas? So for the expected value of this sample mean is going to be equal to mu. It's always the same. But the standard error of this sample mean is going to be equal to the population standard deviation divided by the square root of the number of samples, so 2. So that's going to give us, if we type that in, 0.57. So for B, they want to know the expected value for 4 pizzas. It's always going to be the same as the mean. But the standard error here is going to be divided this time by the square root of 4. And when we type that into our calculator, we get 0.4. So compare the expected value and the standard error of those. So if we look at it, the standard error actually decreases while the sample size increases. So the standard error decreases while the trials increase, which makes sense. The more you do, the closer you're going to get to that sample distribution. Go ahead and give these two a try. Press play when you're ready to see the solution. So that's great, because then we can apply the central limit theorem for the sample mean. And so what that means is we can actually approximate it with the normal distribution as long as the n is greater than or equal to 30 or it's normally distributed. So the only difference when we're looking at our z here is that we would normally do, the raw value, the mean, and then the standard deviation. We just need to make sure that we're using the standard error of the sample mean. So we're still talking about those same pizzas. So we know that it's normally distributed with mean of 16, standard deviation of 0.8. But now they want to know the probability that a randomly selected pizza is less than 15.5. So they're just doing one single pizza. So nothing has actually changed there. This is exactly like the previous examples we've seen before, 15.5. So we want to know the probability. So we've got our score. So that's norm.dist. The x is 15.5. Our mean is 16. Our standard deviation, we're only talking about one pizza, so it's 0.8 and 1. And so we get the probability here is 0.26, and then 5.9 bumps up 6.0. Now, what is the probability that two randomly selected pizzas average less than? So now we're talking about the sample mean are less than 15.5, and our n is 2. So when we type this in, essentially the only thing, and we're still less than, so we're still going in this direction. The only thing that's going to be different is instead of our standard deviation being 0.8, it's going to be 0.8 divided by the square root of 2, because that is the standard error, the standard deviation for the sample mean. And so we end up getting 0.1884. So then if we were to do, okay, for 4 randomly selected pizzas, again, it's less than, so we know that we're good with the average there. The only difference is going to be the square root of 4, and we get 0.1057. So comment on these. So let's see here. So the probability that the pizza is less than 15.5, remember, we don't want it to be less than 15.5. But the probability that it's going to be less than 15.5 is lower. There's only a 11% chance it's going to be lower with 4 pizzas, but it's a little bit higher with 2 pizzas, which again confirms what we already knew, which is that the more samples that we take, the more it becomes normally distributed. Let's do one more example before you do a couple U-tries. So Anne has a marketing campaign going on. Before the campaign, they spent an average of 4.18 on iced coffee and standard deviation of 84 cents. She reports that based on 50 customers after the campaign, this is how much they spent. If Starbucks chose not to pursue the campaign, so they're not pursuing it, how likely is it that customers will spend an average of 4.26 or more on coffee? So if they're not pursuing it, that means that the mean is still 4.18 and the standard deviation is 0.84. Now, the average of people, let's use those 50 people again. What is it greater than or equal to 4.26? That's what we want to know, $4.26 or more. So remember, that's or more, that's this way. And Excel always gives us this way. So we know it's going to be 1 minus. So we're still talking about those 50 people. So we know it's 1 minus because it's the other direction. Oops. So our x is 4.26, our mean is 4.18, but our standard deviation is 0.84 divided by the square root of 50 people. And so we see that it is 25%, about 25%. So 25% likely. I mean, that's pretty likely. Maybe they don't want to invest in the campaign. They're pretty happy with that number. Go ahead and give these a try. Press play when you're ready to see the solution. And there you go. And we're going to stop there and we'll continue with our next section in the next video.